Okay, so here in 3.2, we're going to keep looking at graphs. First, just looking at an equation. So this is just an example of one of these linear equations in two variables that we've been looking at. And what makes these equations more complicated than some of the equations we've seen before is these have more than one solution. So take a second, think about some different things that would make this true. One thing that would make this true is if x is 0 and y is 5, that is one possible solution to this equation. But there's other ones. Like any two numbers that add to 5 are going to make this true. So like 3, 2 is a solution. 5, 0 is another solution. And then there's more than that. Those are just sort of our nice positive integer solutions. But if we start thinking about things that are crazier than that, like I could have negative 5, 10. That satisfies this two variable equation because negative 5 plus positive 10 is positive 5. That works. I could have things like this. I could have 5 halves plus, comma, 5 halves. 5 halves, 5 halves, because 5 halves plus 5 halves is 10 halves, and that's 5. And then, of course, you know, there's an infinite number of these. So I can have crazy things like negative 1,000, positive 1,005 is a solution. So this has an infinite number of solutions. This has infinite solutions. And this is back in the day, so in like 1500, before we had this nice method of graphing, this was just sort of the end of the story. Like, okay, yeah, there's an infinite number of things that add up to 5, that's cool. But once we have this idea of graphing, something exciting happens. All of these solutions can be represented on the coordinate plane, as ordered pairs. So let's go down. I'm going to scroll down a little bit here. And what I'm going to do is just take some of those ordered pairs and graph them. So, for example, we had 0, 5 over 0 up 5. That lives right there. 0, 5. I have 3, 2 over 3 up 2. And this is something you should be very comfortable plotting points like this after going through 3.1. Negative 5, 10, I'm going to be a little bit off my graph, but that's okay. Negative 5, positive 1, 2, 3, 4, 5, 8, 9, 10. So somewhere right up around here. And now you can see something a little exciting is happening. 5 halves, 5 halves. That, let's see, so 1 half, 2, 3. So like 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 5 halves is the same as 2.5. So I would have this point, 5 halves, 5 halves. Now what happens is as I keep graphing these, it's not a coincidence. If you kept finding solutions for this, it would turn out that all of these lie on a perfectly straight line. And so here I can use my fancy computer here to draw a pretty straight line. So this nice straight line goes through all of those points. And that is going to be true for any equation in two unknowns. And this is a big deal. So for any linear equation in two unknowns. So for a linear equation in two variables, the solutions, so the ordered pairs, that satisfy the equation the equation will always lie on a straight line. And this is a huge deal. So this means instead of this impossible task of listing every single ordered pair that makes this true, I can just draw this picture. And what this picture is a picture of every single point that satisfies this line. So not only do all these ordered pairs make that equation true, every other ordered pair on this line, assuming I've drawn it perfectly, like if I look at this, it looks like -1, 6 is on that line. And it turns out -1, 6 does also satisfy my equation. So all these points formed this line, but then every single point on this line satisfies my equation. I'm going to scroll down a little. So here's what I'm talking about. Every solution to my equation is on this line. Every solution to my equation is on this line. And every point on this line is a solution to my equation. That is a huge deal. So I have these two things that are true. Every solution to my equation is on this line, so that means every single point on that line, every single solution will lie on that line. I'm not going to have some point down here that makes my equation true. And every single point on that line is a solution. So, whoops. Okay, so here, every solution to my equation is on this line. Every point on this line is a solution. And that's not all. I also have every point that is not on this line is not a solution to my equation. So every point not on this line is not a solution to my equation. So what this tells me is this line is a total characterization of the solutions of this linear equation in two variables. Every point on this line is a solution, and every point that is not on the line is not a solution. Scroll down a little here. So this perfect picture of all these solutions is called the graph of the solutions. So this is called the graph of the solutions to the equation x plus y equals 5. And so every time you graph a line, what you're graphing is all of the solutions, all of the ordered pairs that satisfy that line. Okay. Let's go on to page 2. Okay, so page 2, we're going to start. So I've talked a little bit about this and why I get excited about this linear equation in two variables. Here is sort of a more formal definition. So a linear equation in two variables is any equation that can be written in the form and here's the form. We have some number, So some constant a times x plus some constant b times y equals some other constant. Ax plus by equals c. There's a lot of other ways that these can be written, so this is just saying they can be written in this form. A, b, and c are real numbers, and a and b are not both 0. So one of them can be 0, and we'll look at some examples of what happens there. It's kind of weird. And another, so you've also maybe seen some other forms. Maybe you've seen y equals mx plus b. Let's just leave it at that one for now. And this is something we'll come to later, but anything that's written in this form could be written in this form by just subtracting mx from both sides, because there's nothing special about this a, b, and c. This is called the standard form of a linear equation, and it's something that often MyMathLab will want you to have your final answers in. So that standard form again is ax plus by equals c. One of the things that makes this a linear equation is there's this structure, but one thing you should be aware of in this structure is x and y, these variables, are not raised to powers, other than 1. And none of those variables are in radicals or in the bottoms of fractions. And the variables are not in radicals or in denominators. And we'll look at some equations later where that is the case, but for now we're going to stay with these relatively more straightforward questions. So I'm going to scroll up a little. Okay. So here are some examples, and I just want to see if these are linear. So this, for example, is a linear equation. It's in exactly this nice form. My a would be 1, so this is a linear equation. This one, and this is an example of how things maybe look a little weird. This isn't in the normal form that I'm used to seeing, but I can actually, this works, and I can put it in that form by doing this. If I want to get all my variables on one side, and this is going to use a lot of the stuff from, I believe it's 2.5, where you're solving things for different unknowns, but now instead of trying to get something isolated, I'm trying to get all my variables to the left side. So I'm going to add 2x to both sides. And what I end up with then is this nice 2x plus y equals 0. And this now is in my standard form. And it's okay for c to equal 0. So what's happening here is I have a equals 2, b equals 1, and c equals 0. And this is linear. Now this is a perfectly good equation, but because y is being squared, this is not a linear equation. So because y is being squared, raised to the second power, this will help me, I don't have to try to spell squared, raised to the second power, this is not linear. So this is not the kind of thing that we're talking about. And because this is not a linear equation in two unknowns, the solutions to this will not lie on a perfectly straight line. Now this one looks weird, and people get stressed out about this, and this being a I'll spoil it here. This is a linear equation, but you only know that from context, because if you just look at this, this looks like the solution to a problem in chapter 2. But here's the way that we're going to think about this here. This is the same as 1x plus, and how many y are there? There's no y, so plus 0y equals 5. That might be a little hard to see. I'm going to go over that here. 1x. So my a is 1, my b is 0, my c is 5. This is okay, as long as my a, b, and c are not all 0. So this is a linear equation, and the solutions to it will lie in a perfectly straight line, and that's something we'll see in a little bit here. Scrolling down. Okay, here is a problem where we're going to be doing some graphing, and we're going to do a lot of different methods of graphing here in chapter 3. We're graphing this equation 2x plus y equals 5. We're graphing this by plotting ordered pair solutions. And there's a bunch of different ways we're going to graph in this chapter. And be aware that it is not a situation where you just pick your favorite method of graphing. You need to know all of the methods. And when the test comes around, I will tell you a method to use, and I need to see that you're using that method, if that makes sense. So here's the deal. This method of just plotting some ordered pair solutions, this is sort of the most straightforward way to do this. What happens is I'm given an x, so this column, these are all my x values. So here, x equals 1. So if x equals 1, I want to find y. And what I'm going to do is take my equation here, 2 times x plus y equals 5. And this is a really powerful thing you can do with any equation like this. I'm just going to plug in that x, and now I'm just going to ask this equation what y will satisfy it. So as I simplify this, I end up with 2 plus y equals 5, and this is something similar to what you did in 3.1. I subtract 2 from both sides, and I get y equals 3. And so now this is kind of the big deal with this method, and this is something we're going to use extensively in chapter 3. I got this y equals 3. That means if x equals 1, then y equals 3. These two coordinates go together to give me a single ordered pair, 1, 3, 1, 3. And now that is a point on my graph. This is an ordered pair that satisfies this equation. So I can graph this, 1, 3, right there. 1, 3. It's a good idea to label these, finding and plotting. I will often on an exam say like label 3 points. I'm going to keep going here. Now they're telling me x equals 0. So I'm going to try to find what y value goes with that. My equation is 2 times some x value plus y equals 5. Now x equals 0. And again, I'm just going to simplify this. This one's nice. 2 times 0 is just 0. So I get y equals 5. And now these, x equals 0, y equals 5, are the two parts of an ordered pair. So I have 0, 5. Over 0 up 5. That's another point on my graph. And one more, x equals 3. So x equals 3. I have my equation, 2 times whatever my x value is, plus y equals 5. In this case, my x value is positive 3. I go through and simplify, and I get 6 plus y equals 5. I'm going to subtract 6 from both sides, and I end up with y equals -1. And so now my ordered pair is when x equals 3, y equals -1. So my ordered pair is 3, -1. And I can just plot that over here, over 3, down 1, because I have -1 there. So 3, -1. And then I'm just going to try to draw a straight line through this. That's pretty good. And so, you can use it. Definitely, it can help to use a ruler for drawing these straight lines because it can be kind of tough. The nice thing is if you label your points and you draw a line, this is not a perfectly straight line, but I can tell that you know what's going on, and that is really what I need to see. Okay, the next couple of pages are some group problems, and so I want you to try these, and I will post the answers online. I'm going to talk about 3 and 4 a little bit here, so let me pull those up. Okay, so the first couple of problems are relatively straightforward. You're just going to be doing what I just did on that previous example, but I want to talk about these a little bit. So on this third one, just to kind of help you get started, this is a lot like that problem I looked at where it didn't look like a linear equation. It was just x equals -2, but it does work. And so what's happening here is they're telling you y equals -2. This is true no matter what x is. So I have this kind of weird situation. If x equals 0, what's y? And people get confused about this, but what's y? Y is -2. So if x is 0, y is -2. If x is 3, what is y? Y is -2. If x is -2, y is -2. So what this is saying is no matter what x is, in this situation, y is -2. And that's a weird line. And if you feel like that's weird, you're not wrong. And we're going to look, these equations get a little strange. There's a couple weird kinds of lines that we'll deal with. The ordered pairs that you'll be graphing here then are 0, -2, 3, -2, -2, -2. And then you just want to find a line that goes through all those points. And then this fourth problem, what I want you to do is graph these two different lines on the same axes. So take this line, this is your first line, and you'll do that one here. And then this second line is going to be sort of similar, sort of different. This line, you're going to find the points down here, and then just graph that line separately. And then you're just going to look at, there's going to be something nice about those two lines. And I will have those solutions up on D2L. As always, contact me if you have questions. Thank you.